All right, today, lesson 48B, proportional relationships and equations, which was our last lesson, but today in more detail. So let's get started. So here we have a table. We've seen this table before. It shows three measurements of a specific type of bamboo comparing the height to the amount of time it took to grow that height. And when we did this, I asked questions like what was the input, what was the output. Remember, the output is determined from the input. If we know the number of days, in this case, we can find the height of the bamboo. And we found all of these things. We determined whether it was a proportional relationship or not. We found the constant proportionality. We found the unit rate. We either graphed it or we answered a question of what the graph would look like, and then we found the equation. Now, when we did all of that, and I want to just get down to the most important piece here for today, and that's getting to the point where we have the equation. So, remember, when you're checking to see if something is proportional with ratios, it doesn't matter whether you go input over output or output over input, but the great thing about output over input is it gives us that constant of proportionality, and in this case it would be k equals 60. And remember, we typically use the letter k to represent the constant of proportionality, and we can also find that constant proportionality on a graph. If we have a graph, it would be at 1 comma, wherever that happens to be. All right. So in this problem, once again I'm showing with a constant multiplier there, we found the constant proportionality. From the table, we can tell that the unit rate is 60 centimeters per day. That 60 is the constant of proportionality. And then from there, we know that the graph has to be linear and goes through the origin since it is a proportional relationship. And our equation should be h equals 60t, and the reason why I'm using h and t is h for height, t for time, kind of makes sense there. And so that's one equation. So could I get you to go ahead and write down that one equation? That's the one that we already found. H equals 60t. All right, but today's focus is trying to go the other direction. Is there another equation that could represent this scenario? So what if we were talking about sort of in the vein of input over output, or going backwards? What might that equation look like? Now, before I call on the people who have their hands up, I want you to listen. Our unit rate from this problem was, one of them was 60 centimeters per, is it day? I've got that covered up here. All right. We've done lots of problems where I've asked you to find both unit rates, right? One of them is 60 centimeters per day. What if you went the other direction? What's the unit rate? And that's an important question. It's 1/60th, what? Days per centimeter. That's the other unit rate. Well, that other unit rate tells us or helps us find that other equation. Here's one of the equations, and that comes from this part right here. So now, what would the other equation look like?
T equals 1/60th h.
It would be t equals 1/60th h. And all I'm doing, I'm showing you via a constant multiplier, even though I've already shown you by going backwards with the unit rate, that would be t equals 1/60th h. Okay? So for the rest of the problems today, we are going to find the constant of proportionality and the unit rate and the equation going both directions. Okay? Going both directions. And I'm showing you here how the ratios of input over output also give us that 1/60th. All right, here's number 2. The table gives the price for a different number of books. I would like you to find the constant of proportionality in both directions, the unit rate in both directions, and the equation in both directions. I'll come back to you in a couple minutes. So we are comparing the price to a different number of books. You're asked to find the constant of proportionality, the unit rate, and the equation in both directions. One direction would be dealing with output over input. And so when I do all of those ratios of output over input, I get 4. So that means the constant of proportionality is k equals 4. A few of you are not using the variable k. At this point, we need to be, if we're answering a question regarding constant of proportionality, let's use the variable k. That way we know what we're referring to. Okay? And that's the constant multiplier as well. Now, the unit rate from that problem going in that direction would be $4 per book, and the equation would be C equals 4B. I am using B to represent books and C to represent cost. You don't have to use those variables. You can use any variables you want. One time I stated we should probably try and use variables that make sense within the problem, but you can use any variables that you want to. Okay? Now, going the other direction, in other words, input over output, or at least thinking of it that way, all of our ratios simplify to 1/4. That is the constant of proportionality going that direction. And the unit rate, of course, as I'm showing you that it's also the constant multiplier, would be 1/4 of a book per dollar. And the equation would be, using those same variables, B equals 1/4 C. Are there any questions on number 2? All right, let's go to number 3. Oh, wait a second. I have one more question. Because we've come across this before. Which unit rate makes the most sense? In other words, what unit rate would be more of a thing that you've heard before?
$4.
Yeah, and that's the direction that you really should try and head. And that's normally the output over the input. Neither one of them are incorrect. They both represent the same scenario, but one makes more sense than the other, okay? Now, let's take a look at number 3. Number 3, it's not very clear what the input or output is on a problem like this one, because this table shows 3 measurements of a special color of paint and comparing the number of cups of blue paint to red paint. Once again, please find both constant of proportionalities, both unit rates, and both equations that would represent that scenario. And I'm using R to represent number of cups of red paint and B to represent the number of cups of blue paint. All right, so going one direction, where maybe thinking that that the output would be blue and the input would be red, you would end up with a constant of proportionality of 2/3. The unit rate going that direction would be 2/3 of a cup of blue paint per 1 cup of red paint. And the equation would be, using the variables that I use, B equals 2/3 R. Once again, notice that 2/3, 2/3, 2/3, all the same. Going the other direction, K would be 3/2. That would be 3/2 of a cup of red paint per 1 cup of blue paint. And the equation would be R equals 3/2 B. Any questions about number 3? Okay, so let's pretend like you thought that the number of cups of red paint is the input and the number of cups of blue paint represents the output. If you thought of it that way, because in this problem, I don't know that one makes more sense than the other, we can easily go both directions. So that's what the graph would look like. And you should be filling that in. And that would be just going 3, 2, 12, 8, 15, 10 for your ordered pairs. In other words, input, output, or cups of red paint, cups of blue paint. Notice that the cups of red paint represents the input because it's on the input axis. Cups of blue paint are on the output axis. Now, if you went the other direction, everything flips. The cups of blue paint now are the input axis. The cups of red paint are now on the output axis. The ordered pairs are all flipped as well. So instead of 3, 2, 12, 8, 15, 10, we end up with 2, 3, 8, 12, 10, 15. So notice that the graphs are basically just flipped versions of each other. Okay? So I'm going to stop for just a second to let everybody get their graphs totally finished. Once again, the graph on the left represents the first way that I dealt with these things. Or the first constant of proportionality and unit rate and equation I gave you. The graph on the right is the second version of what I gave you. And once you get both those graphs finished, can you go ahead and do all 3 parts for number 4. So in number 4, we have a straight XY chart or table. Typically, in situations like that, typically the X represents the input and the Y represents the output. Okay, and we've talked about that idea before. So going that direction, K would be 1/5, and that is how we write the constant of proportionality. The unit rate would be 1/5 of a Y per 1 of X. And the equation would be Y equals 1/5 X. The other direction, thinking that maybe X is the output and Y is the input, K is equal to 5. The unit rate would be 5 X's per 1 Y. And the equation would be X equals 5Y. Okay. Hopefully that's all clear. Let's go to the back side of our notes. And in this problem, I don't know that either unit rate makes any more sense than the other one. So number 5 goes like this. Jose paid $6.25 for 5 pounds of candy. We're still doing the same thing. We want to write the constant of proportionality, the unit rate, and the equation. But what we're going to do is we're going to fill in a table to help us out with that. Okay? So we have a table that starts like this. Now, one thing that we know is we know that $6.25 is what the cost is for 5 pounds of candy. So that would give us this ordered pair right here. Now, if we think about this, you need to know the number of pounds of candy to find the cost. So the number of pounds of candy is the input, the cost is the output. Is there one other, because you'll notice in your table there's space for one more ordered pair. What other ordered pair do we know, or what other situation might we know from that? Turn to your shoulder partner and have a quick conversation. And that would be this. If he didn't buy any candy, it doesn't cost anything. Now the reason why I want to use that one is simple. As remember, we're trying to think of this in terms of a proportional relationship. Okay? So we're going to do this one together. So I'm going to use P to represent pounds of candy, C to represent the cost. And so the constant of proportionality, going with the input being the number of pounds and the cost being the output, 6.25 divided by 5 is 1.25. So that's the constant of proportionality going that direction. The unit rate going in that direction would be $1.25 per pound. And using the variables that I used, C is equal to 1.25p. We're not doing anything different here. The only thing that is different, I suppose, is that I'm giving you a sentence instead of a table. But we're going to create a table so that we can then do the same thing. Now going the other direction, thinking that, well, I want to find pounds per dollar, well, that would be 5 divided by 6.25, and that would give us a unit rate of 4/5 or 0.8, depending on how you look at that. And that would be 4/5 of a pound per dollar, or 0.8 pounds per dollar. And the equation would be P equals 4/5 C. So in essence, we're doing the same thing here. And obviously, in this word problem situation, one unit rate is going to make more sense than the other. And I think it's obvious that it's $1.25 per pound. Okay? All right, I would like you to go ahead and do number 6 and number 7. And then we'll compare with our shoulder partner. Number 6, Aaliyah drove 119 miles in 7 hours. So we know that piece of information that we can log in our table. I mean, there are lots of things we could add in there. Assuming that she's driving at the same rate, we could put 14 hours and 238 miles if we wanted to. But we also know that if she hasn't driven at all, she's driven 0 miles. So that's a nice, easy one. Going one direction, and I'm using T for time, D for distance. The constant of proportionality is 17. I'm going with distance over time, thinking that distance is output and time is input. The unit rate is 17 miles per hour. The equation going that direction is D equals 17t. Going the other direction, K is 1/17. That's 1/17 hours per mile for the unit rate going that direction. And equation will be T equals 1/17 D. Number 7. And I think it's obvious 17 miles per hour makes the most sense. There are 24 inches in 2 feet. If we have 0 feet, we have 0 inches. You could go with 6 feet, 72 inches if you wanted to. I'm going to go with F and I for my variables, thinking that inches is output and feet is input. K is 12. Unit rate is 12 inches per foot. Equation is I equals 12F. Going the other direction, K is 1/12. The unit rate going that direction will be 1/12 of a foot per inch. And F equals 1/12 I. Any questions about what we've done so far? Okay, so now we're just going to restrict it to a scenario, much like 5, 6, and 7. But we're just going to try and jump straight to the equation. So number 8 says Jamie ran 12.5 miles in 2.5 hours. Write an equation that represents how far in miles M she ran per hour H. Let's see if you can figure that out. Now, if we read the second sentence carefully, we should understand that we're finding essentially the unit rate of how many miles per hour. It clearly says that right here. We're trying to figure out how far M she ran per 1 hour. So we're not going both directions on this one. We're going that direction on this one. Anybody have it? What'd you get? H equals 5M. Shouldn't it be M equals something H?
Yeah. I wasn't sure because I put hour like it was like 1 hour equals 5
Well,
miles.
so if you're not sure, then you could probably go with a table like we did in 5, 6, and 7, and maybe that would help you lead you down that direction. But the unit rate here is 5 miles per hour, and since it's 5 miles per hour, that would mean M equals 5H. To find the number of miles, you multiply the number of hours by 5. In other words, the number of the amount of miles is always 5 times as big as the number of hours. Okay? All right, go ahead and do the same thing for number 9 and number 10, and then we are finished for today. So what was given to us originally for number 8 was this. H equals 5M. Anybody know how we can check to see which one is right?
If we take what we have for the miles already, 12.5, and multiply it by 5, it should equal 2.5.
Yeah, and that's clearly not correct. 2.5 is not equal to 5 times 12.5. However, if we take instead and we substitute it here and here, that is a true statement. So that's one quick way. If you're not 100% sure, substitute the values back into what you get. It should work. If it doesn't, it's not the correct equation. Okay? All right, so let's take a look at number 9. Number 9 states that Ben bought 1.6 pounds of lunch meat for $14.40. Write an equation that represents the cost C per pound P. So that's the direction we're going. We need to find the unit rate for that, which is 9, I believe. And so that would give us an equation of C equals 9P. And once again, if we substituted these values in, this in for P, this in for the cost, it better make a true statement, and it does. So we know we're going in the right direction. Number 10, now we're taking a situation with fractional value. So Marshall walks 1/3 of a mile in 1/5 of an hour. Write an equation that represents how far in miles she walked per hour H. That tells us what direction we need to go. We need to find the unit rate, which is 5/3. And so M is equal to 5/3 H. And once again, if we substituted these values in, it better make a true statement, and it does. 1/3 is equal to 5/3 times 1/5. Okay? All right, we are finished for today.